Alright, today we're going to be looking at electron configurations. Remember that electron configurations are contingent on the rules, on these following rules. There are three rules that govern how we describe electron configurations. First rule is called the Aufbau principle. Aufbau principle basically states that an electron occupies the lowest energy level that can receive it. The second rule governing electron configuration is the Pauli exclusion principle. Pauli exclusion principle formally says no two electrons in the same atom can have the same set of four quantum numbers. What I would like you to know that means is that electron pairs will have opposite spins. So in an orbital, the two electrons that are within an orbital will have opposite spins. According to, and then Hund's rule is the third rule governing electron configuration. Hund's rule basically says that orbitals of equal energy are each occupied by one electron before any other orbital is occupied by a second electron. So basically, fill in order is Aufbau. Second, Pauli is saying if two electrons are together, must spin OPPOSITE. So one's going one direction, the other's going the other direction. And then the third thing, you have to fill orientations in one direction before filling the opposite. Alright, so now without seeing this doesn't make a whole lot of sense, but let's go ahead and look at some of these and look at some of the guiding things. Alright, first thing I want us to know is that we have for this particular thing, helium should actually be over here. Alright, helium, and that's going to be 4.03, and this whole section we will call the S block. Change colors real quick. This section and 71 and 103 down here are part of the D block. Now D block has something special because D blocks are actually, you started on the, we have 1, 2, 3, 4, 5, 6, 7 quantum levels, but the D block is actually filled on the quantum level before it. So this would be 3D, this would be 4D, this would be 5D, and this will be 6D. The same thing happens here on this section. Let me get a pen. This section down here is actually, this section is called the F block. And the F block, we are going to fill this one on the 4th level, so this is 4F, and we'll fill this one on the 5th level, this is 5F. Do realize, though, that these are actually on period 6 and 7. This is actually on period 4, but the place that the electrons are going are on the 3rd until you get to there. You don't have enough electrons to fill into there until these. All right. And then the last section, the last block, let's see if I find a color that will stand out. Let's use blue. The last block is this section over here, and this is the P block. And this one is pretty much normal. This is 2P, this is 3P, this is 4P, 5P, 6P, and 7P. This would be 1S, 2S, 3S, 4S, 5S, 6S, and 7S. All right, so we are going to be using this table to come back and refill in some certain things. So as we go through this lesson, you will want to have a periodic table in front of you. I will not be able to go back and forth for a periodic table. I will try my best to do this just so that you can kind of see what's going on as we do it, but just follow along. All right, so we are looking at a couple of things, and the first thing that I want us to look at is this concept of what are the actual configurations that I want us to know. Well, what do we know already? At this point, everyone in this class should be able to answer these three without really a whole lot of thought and a whole lot of effort. So a Lewis dot diagram. A Lewis dot diagram for arsenic, what is the first thing we're going to write? Well, we look up the symbol for arsenic, which is AS. The next thing that we were going to explore is that arsenic is in family or group 5A. So what does that tell us? That it has 5 electrons around it. So I'm going to go ahead and fill my electrons. 1, 2, 3, 4, 5. So I have one set of paired electrons and 3 unpaired electrons. The next thing that we could do is, well, how many electrons are in the valence shell? We already determined that. 5. We have 5 dots, 5 electrons. And what valence shell are we dealing with? Well, arsenic is in period 4, so that means it's in quantum level 4. All right. Now, let's go ahead and work the rest of this. So in order to do this, remember we're dealing with arsenic. The first one we're going to talk about is regular order configuration. So let's go back to our periodic table. Well, let me erase a couple of things just because it's in the way a little bit. But so starting off here, we are looking at arsenic, so we're looking at this element right here. Easiest way for me to explain how to write a regular order configuration is really just to have you count the elements. So we're looking at arsenic right here. We have to get through all of these other elements before we can get to arsenic. So we are covering 1s1, 1s2. So we have 1s2 is completely filled. All right, next step, starting with lithium. Lithium goes 2s1, 2s2. So that is completely filled. Start over here, 2p1, 2p3, 2p4, 2p5, 2p6. So this will be 2p6. Notice at this point we have only had S's and P's. Same thing with row 3. There's no D block there yet. So arsenic is still right here, so we have to go through this whole row. So we have 3s2, three p6. And then now we are getting a little bit closer. Arsenic is on the 4th period, but we still have to go through all of this. So we have 4s2, and then now look what happens here. It's not 4D, it's 3D. So it's 3D, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So arsenic is way over here, so we have to go through all of these elements. So next thing I'm going to write is 3D10. Then I'm going to go ahead and go into, now we're into 4P. And how many spaces are we into P? 1, 2, 3. So it is 4P3. All right, so looking at this, what I want to be able to do is I want to take this information and I'm going to move it to the other page. So I'm going to pause again and we'll come back to the other page where we're. So from this point, we no longer need to go back to the periodic table. We can do all the rest of this with just the information that we have available. All right, so regular order is like this. And notice we kind of almost are in counting order, but we have ones. We have our 1s, our 2s, our 2p, 3s, 3p, 4s, but then we jump here to this 3d. This 3d sometimes presents a problem. So we have this other way that we refer to it is called expected order. And all expected order does is it groups it by quantum numbers. So we have 1s2, 2s2, 2p6, 3s2, 3d10, 3p6, 4s2, and 4p3. For orbital notation, what we have to do is we have to remember what was happening with the orientations and how many orientations we have of each shape. So I'm just going to make some notes over here on the side. So for the S orbital, how many orientations or how many directions can a sphere face? All right, 1. For D, how many orientations did we say we had for D? 5. For P, we had 3 orientations, and for F, we had 7. So this is something key to now is we're going to take this information the regular order configuration and make it a little bit more graphic to, instead of identifying the electrons with numbers, we're going to identify them with arrows. All right, so backing up just a moment. One of the ways to check yourself on this, we know that arsenic is atomic number of 33. So if this is a neutral atom of arsenic, then it's going to have 33 electrons. So 2 plus 2 is 4, 4 plus 6 is 10, plus 2 is 12, plus 6 is 18, plus 2 is 20, 30, 33. So 33 electrons. So we have the same number of electrons in that, and that lets us know that this is our atom. Now let's go ahead and do orbital notation. So we're going to start off with our 1s. 1s has one orientation. And remember our rules. Going back to our rules and my little shorthand of the rules, fill in order. Fill in order. So we're going to fill from low to high energy. Second thing, if two electrons are together, they must spin opposite and fill orientations in one direction before filling the opposite. All right, so let's go back with those rules in mind. So for our 1s orbital, we have to fill it first because that is our lowest orbital. So we have 2 electrons to account for. So we have one going in the up direction and one going in the down direction. Our next orbital is 2s. How many orientations? 1. So that means we're going to have an arrow up and an arrow down because we have 2 electrons here. Next thing is we have 2p. For p, there are 3 orientations, so I'm going to draw 3 blanks. And I have to fill them in order. I have 6, but just following the rules, I should do all of the ups first and then come back and do the downs. All right. After 2p6, we have 3s. We have one arrow going up, one arrow going down. Then we have 3p. 1, 2, 3. It's going up, going up, going up, down, down, down. And that attributes for my 6 electrons. Now, after 3p comes 4s. 4s has one up, one down. And then, this is where it gets tricky. We have 5 orientations for D. 2, 3, 4, 5. So 3D, and then we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then our last one, we have 4p, and there are 3 orientations in p, so we have 3 different spots to put 2 electrons and I. So what's wrong with what I did right here? This arrangement actually breaks Hund's rule. Going back, Hund's rule says that each energy level are occupied by 1 electron in any orbital before it's occupied by the second electron. So in other words, I have to fill all of the ups before I start doing the downs. So let's go back and fix this. So the place that I have my error is this down right here. Just trying to cheat and not have to erase as much. So let's go back and put my arrow in the right spot. Now I have satisfied Aufbau by filling from lowest to highest. I set aside alpha from filling lowest to highest. I've set aside Pauli by having opposite spins wherever 2 electrons are required in the same spot. And then I followed Hund's rule by filling all of the ups, so that having the maximum lone electrons. Why is it important to have the maximum number of electrons that don't have an opposite by it? Remember that electrons are all charged negatively, so whenever you have 2 of them occupying the same space, even if they're in opposite spins, they're going to still experience some repulsion, so it takes a lot of energy for them to be able to be held in place there. Alright, so moving on. Let me erase something real quick just to give myself a little more room. Now, we move to noble gas. And when we're looking at noble gas, what we have to remember is noble gas configuration is a shorthand method for interpreting this. So what we're going to do now is we're going to go back to our periodic table. This is the only reason why we have to do this. We are looking for the noble gas on the period above the element we are working with. So again, what element are we working with? We are working with arsenic. So I'm going to look at my arsenic, which is right here, and I want to know what noble gas is immediately above it. So the noble gas that is on the row above is argon. Alright, now with that in mind, what I need to know is what is basically what noble gas configuration does. It allows us to eliminate part of all of this. So if I went through and identified argon, argon is 1s2, 2s2, 2p6, 3s2, 3p6. Alright, so that means all of this information tells me argon. Alright, and it's important that we always put argon in brackets, put the noble gas in brackets when we're doing noble gas configuration. So that is argon. So all of this information again is telling me argon. Alright. So when I go to write my noble gas configuration, I'm going to start off by writing my noble gas that's on the row above it, argon, and then what I'm looking for is what makes this element look different than argon. Well, the things that make it look different: 4s2, 3d10, 4p3. This is what it has This is what arsenic has that argon does not. Alright, now for valence shell configuration, one of the things that we need to remember, valence shell has an octet. Octet means that the number of electrons, the maximum number of electrons that a valence shell can have is 8. So if we consider the orbitals, we can have in S we can have 2 electrons. In P we can have have 6. In D, we can have 10, a maximum, and in F, we can have a maximum of 14. What orbital or combination of orbitals gives you a total of 8? The only one that can give us a total of 8 is a combination of S and P. So we are looking for the highest S's and P's that are on the same level. So we have 4s and 4p. So valence shell configuration is going to be 4s2, 4p3. Now, 2 plus 3 is 5. So remember, we had 5 electrons, and then we had 5 electrons around on the Lewis structure. The other thing to notice is we have one set that's paired and 3 individuals. One set that's paired, 1, 2, 3 individuals. Always going to fill the maximum number of opens before we close it off. Alright, moving over. Now, what I just showed you there doesn't always work. If it's only got an S and we only have 2, then you're going to have 1 in here, 1 there. But in general, it works for the most part to kind of see that, especially when you're dealing with the S and the P, and there's an odd number in the P. All right, so let's do it for calcium. I mean, not calcium, potassium. All right, so first thing I want to know from the periodic table, potassium has 19 electrons. This is what we're trying to accomplish. Potassium is also in group 1A. So a couple of things that we can already identify with this. Start down here with our Lewis structure. Potassium, group 1A, it has 1 electron. It has 1 electron in its valence shell, and potassium is in N4. All right, so let's do this. Is potassium lower than the first level? Yes. So you're going to go 1s2. And I would recommend trying to do this on your own first, so pause the video right here and then see if your work matches mine. Alright, so coming back, hopefully you will match what I did. So going a little bit further on row 2, does potassium move all the way across row 2? Yes. So we have 2s2, 2p6. And then we look at row 3. Yes, we complete row 3, so 3s2, 3p6. Now is where it starts getting tricky. Right now, at this point, what element are we at? That's argon. All right, so potassium in relation to argon, what does potassium have different than argon? Potassium has a 4th energy level with an s orbital and 1 electron in it. All right, so orbital notation. Up, down, up, down, up, down, up, down, up, down, down, up, 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 down, 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 up. All right. Now, the easiest way to verify that you have the right one, and this will be a question that you will see in the future, you're gonna see an orbital notation, something like this. It may or may not have these letters down there, but it'll have dividers letting you know which ones, where it's divided up at. So what you'll need to look at is, they'll say, what element is this? All right, what? Well, we know that this is potassium, but how do we know? Well, because when we go back and we count the arrows, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. We have 19 electrons, and then we can say what neutral atom has 19 electrons? Well, potassium. Potassium has an atomic number of 19, so therefore that tells us that a neutral atom, potassium, has 19 electrons. That doesn't necessarily work for ions. Ions are going to look like a noble gas. They will always gas. All right, now getting to our noble gas configuration. We've already determined this. This is argon, so our element that we're putting here is argon. And then what's different about potassium than argon? 4s1. And then even easier, valence shell electrons. What is our highest S or P? S and or P. 4s1. All right, one electron there, one electron there, one electron there. All right, let's try one more or two more. And again, I'm not going to flip back to the periodic table on this one. Hopefully you'll have a periodic table going through. So we are looking at barium now. Barium is element 56. So that means we have 56 electrons. Barium is in column 2. Whoa. Let me take care of that real quick. Element, it's column 2A, and it is in row 5. No, row 6. So just from that information, I already know some things about barium. And I mean, I can pretty much go ahead and don't need to count the electrons yet, but since I know it's in row 6, I know that it's going to have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, and then now we start our sixth quantum level, and we need to look at where barium is. Well, barium's in column 2A, so it is only going to have 6s2. All right. Now that's regular. What changes for expected? All we do with expected is we're going to group the numbers by their quantum number. So that means I'm going to move this 3d10 in between 3s2 and 3p6. Because if you look at the shape of the periodic table, it kind of lets you know that you have to cross that D before you can start going into the P. All right? And then the other change will happen here is this 4d10 will come in and go where the 3d10 used to be. And then that's your expected order. You could rewrite it out so it looked like 1s2, 2s2, 2p6, 6, 3s2, 3d10, 3p6, 4s2, 4d10, 4p6, 5s2, 5p6, 6s2. All right, orbital notation. Oops. All right, everything's pretty much the same up until this point. So after 4s comes 3d. We're going to do this based off of regular order. So regular order, a D has 5 orientations. So this is 3D. Then we have 4P, 1, 2, 3. And then we're coming to our 5th row, 5S, 1, 4D, 1, 2, 3, 4, 5, 4D, 5P, 1, 2, 3. And if you have trouble distinguishing your breaks for your groupings, don't be afraid to draw some little hash marks in between it just so that you can see. And then we go to 4S. I mean, not 4S, 6S. All right, so just accept that all of these are full, and I'm going to start right here at 4D. Well, we'll start at 5S. How about that? That one's full. We would fill all of them in the up, then in the downs. Up, up, down, down, down. All right, now, once we get to 6S, this one is full, but I still fill up, then down. And then that is that. Noble gas. So find barium. Barium's in the 6th row. The noble gas on the 5th row is xenon. So our noble gas configuration is going to be the highest level, and in this case we don't have a P to go with it, so our noble gas configuration is xenon 6S. All right, now just kind of finishing this one off, you can do xenon on your own. Actually, I'll kind of guide you through that one as well, but we're going to take some shortcuts on that one. All right, valence shell configuration is just going to be the 6S. Valence shell, we are in N6. How many electrons do we have in our valence shell? Well, sorry, 6s2. I forgot that. We have 2 electrons, so when we draw this, we are dealing with barium, if I remember, yes. We're dealing with barium, so it's going to be Ba, and there are 2 dots. All right, moving on for xenon. All right, xenon's on the 5th period all the way at the end. So 1s2, 2s2, 2p6. Try this on your own before you watch me do it, and then check to see where your answers don't match. 2p6, All right, so that's what you should have gotten for xenon's regular configuration. If you were to do expected configuration, again, you're just going to move, let me grab a different color. You'll just move this in between the 3s and the 3p, and then you will move 4d in between where that goes. All right. Orbital notation, again, try it on your own, then check your answer. All right, so we are at our last one here, and I just wanted to make sure that we followed all the rules. We filled from low to high, that's off bow. We filled, every one that's filled is opposite spins. And now we come to our last one for Hund's rule. You're going to fill in all the up direction first, and then you'll fill in the down direction. And so that gives us the 5p6. All right, looking at noble gas configuration, again, you want to look at the noble gas that is immediately above xenon. You cannot use the noble gas that it is because that doesn't tell us anything. So just above xenon we have krypton, and that represents everything up to that 4p. So everything, so this is all the new stuff, so it's going to be 5s2, 4d10, 5s2, 4d10, 5p6, and then valence shell configuration, the two highest S and P, 5s2, 5p6. Valence shell is going to be N5, and number of electrons in the valence shell, 2 plus 6 is 8. Our diagram, eight electrons orbiting around. Email me if you have questions and go from there.